All right, so Chemistry 3102. This is your week 9 assignment. So I know that some of you are doing the recrystallization experiment during week 9, but if you look at our schedule during week 9, underneath experiment 3.4a and b, and that's for group B, you'll see technique M and technique P, and that is covered in this worksheet. So it's an IR and MS worksheet that everybody has to complete. It has the same due date for everybody in the class. So for everybody, this will be due on March 26th. Not March 29th. March 26th at 11:59 p.m. Okay, so everybody has to have this completed within the next 2 weeks. So what you're going to do is you're going to print it out, and then you're going to fill it out, and then you will submit it as a single collated PDF to Canvas. So let's take a quick peek at the instructions. It says here you're given infrared spectra and mass spectra. Annotate the spectrum or spectra, depending on whether you have 1 or 2. I think they all have 2. Showing key absorptions on the IR. In order to determine what the compound is, I've given you a list of possible unknowns on the last page. There are more than enough unknowns, and there's only 1 compound per spectrum or pair of spectra. And so you have to be able to figure out which one is going to be correct. Also, many of the compounds have more than 1 functional group. So you might have, let's say, an alkene and an alcohol, or an alkyne and a carboxylic acid in the same compound. So you have to be aware of that. All right, and it says here that while some of the spectra might fit with more than 1 of the choices, there is a best choice for each spectrum. So you got to pay attention to the details. We have a whole host of functional groups that can come up: amines, alcohols, alkenes, alkynes, aldehydes, carboxylic acids, the nitrile, ester, aromatics, ethers, and ketones. So we have the whole plethora, or the whole gamut of functional groups. Also, you have to properly annotate the spectrum to receive any credit. If you just write down the name of the compound, that will not suffice as answering the question. You have to show that you understand what is going on and that you're able to annotate. For example, it says, let's say, since you have sp3 hybridized carbon hydrogen stretching, you don't include that. But let's say you had sp2 or sp hybridized carbon hydrogen stretching, you would include that. Okay, so here's an example. Let's say you had this compound here. It's just an infrared spectrum. And if you take a look at the line around 3,000 centimeters to the -1, and if you draw maybe another line here around 1,700 centimeters to the -1, you see that you have an absorbance around 3,100 reciprocal centimeters, which indicates an sp2 hybridized carbon hydrogen stretch. You see that you also have a weak stretch around 1630-ish. Okay, so this is going to be an alkene carbon-carbon double bond stretch. And so again, you would want to point those out. You can either draw an arrow to it the way I have here, or you could circle the peak like that. Okay, so then what functional groups are in the compound? Well, it's an alkene, right? And what's the name of the compound here? The name of this compound is cyclohexene. If you go to the very end of the assignment, so this is the very end of the assignment, you see that I have a whole Can you guys see my screen still?
Yeah, we can see it.
Okay, good, thanks. So you have a whole bank of compounds to choose from. So you're not just choosing out of thin air. You have all of these different compounds. Say, for example, this one has a carboxyl group, so a carboxylic acid and an alkene in the same molecule. What else? This one has a nitrile and an aromatic. So you have all of these different compounds to choose from. Okay, you are not going to use all of them. You will use some of them. Okay, I have all these different choices here, but again, there's a best choice for every example, for every possible question. And there are a total of 10 problems. So if we go back to number 1, you see that we have an infrared spectrum here. I want to point out something to you, that you see some of the signals or some of the peaks in the infrared will be crossed out with a red X like that. The reason why I've crossed some of these out is because I don't want my students getting confused when the signal is unimportant. So when I cross it out, it's because the signal is noise. And if you mean like I don't hear any sound, like what does that mean? Noise simply means it is not pertinent to the actual functional groups in your compound. So I crossed it out so that you could just ignore it and focus on everything that's not crossed out and try to identify, you know, absorbances that you see that aren't crossed out. So here's the first one. We have a beautiful IR, and then we have an MS to go along with it. We have the molecular ion at a mass over charge of 98. You'll want to try to identify, for example, the base peak. And if there are any other fragments that you can identify, that you're able to identify, especially after today's lecture, I'd like you to try and do that, because you want to provide some kind of rationale for the name of the compound and its structure. And then, of course, you're going to include the functional groups as well. All right, let's move on to the next one. You see that I didn't cross out anything in the IR. In the mass spec, you can see there's something interesting here. And again, of course, you have to include the functional groups that are present in the molecule, the name of that molecule, and the structure, which again, you're going to get from the bank of compounds found at the very end of the document. If we move on to number 3, you see that I have crossed out 2 sets of peaks here, which are unimportant. Again, what that means is you need to focus on the other absorbances. Okay, you can just completely ignore those ones that are blocked out. Then we have an MS. You can see there's something interesting here. We have our molecular ion at 136. Problem number 4. See, there's also something crossed out here that you can ignore. But you see there's lots of other interesting absorbances here. Maybe even down here. And there's the molecular ion. Got a mass of 117. Number 5, nothing crossed out there. Have a good molecular ion. Number 6. Okay, nothing crossed out in number 6. Pretty simple mass spectrum here. We have a molecular ion, then we have one fragment, or one base. The base peak is basically the only fragment in there. The next one, you notice that there's a big peak that's crossed out in there. Now, if you're thinking, what is that? Well, what's causing that? It's probably an impurity that was run in the sample. Most of the spectra that you see in a textbook are probably sanitized versions of what a lot of spectra look like. So they might erase some peaks to make it easier for students. But this is more of a, real approach. And I'll just give you a little bit of a hint on this one. It's that it's possible to have weak signals buried in there, okay? So sometimes you can have signals that are buried under big old impurities like this. So I'll just leave that there as food for thought. You see that in number 8, I've also crossed out something that you can ignore here. That's also some noise. You can probably recognize that functional group pretty quickly. We have a nice molecular ion there. Number 9, nothing crossed out there. Another nice mass spectrum. And in number 10, also, this is the last one that I crossed something out that is unimportant. As you can see, we have some big absorbances, big one there, and some interesting signals there. And we have a really good molecular ion there. And that's it. So you have a total of 10 problems. Now remember, you can't just put an answer. You can't just say, benzoic acid, carboxylic acid, and then draw the structure. You've got to put those things in there, but you also have to annotate the spectra, right? If we go back to the first example, you have to identify the signals. And also in the mass spectra, I would like you to try to identify fragments. For example, this base peak, what is it? What is it? And if you're confused about mass spec, that's going to be mostly the focus of today's lecture. Okay, so that's the actual assignment itself. Again, it's going to be due on March 26th for everyone, no matter if you're in Group A or Group B. I'm going to post an announcement to Canvas to remind you about this. Please submit it as a single PDF that's black and white. Don't just send us pictures. Pictures are actually a lot harder to discern what's going on in than a black and white PDF. Are there any questions about the worksheet before we take a look at some new signals in the IR that we didn't discuss in lecture? Are there any questions about this? All right. Well, from there, let's move on to IR. And again, as I told you, I'm not going to go over the theory of IR because most of you are currently enrolled in the lecture course, Chemistry 3101, and those of you who are not enrolled in that lecture course would have passed Chemistry 3101. So most of the information that you need to know about IR has already been covered in that class. So I'm not going to reinvent the wheel or reteach something that you should have already covered. For example, before you step into working on the actual worksheet itself, I highly recommend reading the background in the lab text. Now you might be saying, well, I read everything that I needed to in Klein. I also recommend taking a look at it in our lab text because our lab text will fill in some of the gaps, a few of the little nuances that you haven't covered, or we haven't covered. Now, one thing that's here, and this is an artifact of previous semesters, pre-coronavirus semesters. This is a dry lab, and there is going to be no attendance. So this one's going to be completely done on your own at home. We're not going to have a lab for this. However, if you are in the lab and you want to bring it with you and ask your instructor, Mr. Mayer or Miss Herring or I, a question about it, feel free to do that. So again, I'm not going to cover all the theory about spectroscopy. We just covered this all in gross detail in the lecture course. We talked about what stretching was, and we talked about scissoring and twisting and how we mostly focus on stretching frequencies. And the same is true in Chemistry 3102. So I'm going to skip through all of these slides and get right down to past the theory. And a lot of these slides you probably notice are duplicates of the slides that we looked at in Chemistry 3101. And I just want to take a look at the functional groups very quickly with all of you. Now, an alkane technically isn't a functional group, but one of the easiest things you can do is to draw a vertical line at 3000. And these absorbances here are the result of sp3 hybridized carbon-hydrogen stretching. So most organic compounds, not all, but most organic compounds that we look at have some sp3 hybridized carbon-hydrogen bonds in them. And so if you have a molecule like this, which is pentane, you see a strong signal just below 3000 for that sp3 hybridized carbon-hydrogen stretching. An alkene, we went over this in the lecture course. You see the alkene carbon-carbon stretch around 1630 right here. You also see sp2 hybridized carbon-hydrogen stretching around 3100. Again, that's why it's really helpful to draw that line at 3000 reciprocal centimeters and look above that. Next, for an alkyne, the carbon-carbon triple bond comes out at around 2150. Don't get that confused with a nitrile. A nitrile is this. Oops, let me clean that up. A nitrile is when you have a carbon with a triple bond to nitrogen. A nitrile, this stretch comes out around 2250. So 2250 for the nitrile, and I have that on another slide. Again, the reason why you want to draw that line at 3000 reciprocal centimeters is because you can see many interesting absorbances above that, right? For example, sp hybridized carbon-hydrogen stretching from a terminal alkyne that's shown here. Alcohols, usually my students are very quick to recognize alcohols. We have broad oxygen-hydrogen stretching between 3200 and 3600 reciprocal centimeters. We also have the carbon-oxygen stretch that occurs between the carbon-all-carbon and this oxygen from the alcohol, which comes out between 1000 and 1250 reciprocal centimeters, so an alcohol. Next, we have an amine. This one has two new stretches that you didn't see in Chemistry 3101. In Chemistry 3101, you would have seen that for a primary amine, you get two medium to weak absorbances around the 3400 reciprocal centimeter region for a primary amine, right? This is a primary amine. We have symmetrical stretching and asymmetrical stretching. But two new absorbances I want you to look for are a nitrogen-hydrogen bend, which is around 1600 reciprocal centimeters. That's for a primary amine only. And then also carbon-nitrogen stretching, which can occur between 1250 and 1000 reciprocal centimeters. So it might be handy to identify that. Okay, again, this one here is only for a primary, but these, and this one is This one here is a primary amine. Then for a secondary amine, we only see one absorbance. Okay, so primary and secondary. And then I also want you to try to identify the carbon-nitrogen stretching if you can. Next, the ketone. We have the carbonyl absorption at 1715. Here we have 1500, 1600, 1700. So this is around 1750. There are no other absorbances of interest here. Of course, you have the ubiquitous sp3 hybridized carbon-hydrogen bonding. But again, you do not have to annotate that in any infrared spectra. Next is the aldehyde, which has the two absorbances for the carbon-hydrogen stretching at 2850 and 2750. So that's these two guys right here. Then you also have the carbonyl stretch around 1725 reciprocal centimeters. Usually the aldehyde CH stretching is a dead giveaway. It's usually pretty easy to see in a spectrum that is an aldehyde. Carboxylic acid, probably the easiest of all functional groups to recognize in the infrared spectrum, since the OH stretching is so broad on account of the fact that a carboxylic acid can form these hydrogen bonding dimers like this, okay, where we have something like this, which, and let me draw a hydrogen bond like this and like this. So since it forms these dimers, we have so much stretching of the oxygen-hydrogen bond that it's really broad signal, all the way from 3300 to 2400 reciprocal centimeters. Of course, you have a carbonyl stretch around 1715, and you can also find carbon-oxygen stretching. An ester is another one that once you get better and better at infrared spectroscopy, you can become very proficient in recognizing esters very quickly. The reason why is because all of the carbon-oxygen single bonds that you see in alcohols, carboxylic acids, ethers, they are not nearly as strong as the carbon-oxygen single bond stretch that you see for an ester. So you see how this is very strong. In fact, it's just as strong as the carbonyl stretch around 1735. So something to keep in mind, again, is that the carbon-oxygen stretching for an ester is really strong. Next, the acid anhydride. This is one that we didn't even look at in chemistry 3101. The two carbonyls, we see two carbonyl stretches for them. We see one at 1760 and the other at 1810. So if we look here, we have 15, 16, 17, 18. So this is around 1760, and this one here is around 1810. You also have a strong carbon-oxygen single bond stretch. That's for these guys here, okay, which is going to occur in the neighborhood of 13 to 900 reciprocal centimeters. So that's this one here. And anhydride is another one that once you become more accustomed to looking at infrared spectra, the carbonyl that gives two peaks is usually a dead giveaway. Next is the nitrile. Sometimes students get it confused with the alkyne triple bond. Remember, the carbon-carbon triple bond in an alkyne is at 2150 reciprocal centimeters. For the nitrile, it's at 2250 reciprocal centimeters. And we looked at the reason why that would be. It's based on Hooke's law. I'm not going to go into that detail right now, but that's the dead giveaway that you've got a nitrile. And then the last one, I think it's the last one I had. No, I have two more. The alkyl halide. This is another one that's not seen in chemistry 3101. If you have a bond between carbon and a chlorine, so this only works with carbon and chlorine, you have a stretch between 800 and 600 reciprocal centimeters. If you have a carbon bromine or a carbon iodine single bond, you do not see it on the infrared because it comes out below the region or below the limits of the infrared spectrometer. So you won't see those. Okay, so a carbon chlorine bond. And then, yes, this is the last one here is the aromatic. Okay, again, as I told you in the lecture class, that the aromatic carbon-carbon double bond stretches, okay, these ones right here, are usually a collection of 2 to 3 signals between 1600 and 1475 reciprocal centimeters. Also, we have the overtones, which students are usually obsessed with, that come out between 20 or 2000 to 1667 reciprocal centimeters. That's these guys here. Those are overtones, aromatic overtones. What else? If you draw a vertical line here, you see that we have some sp2 hybridized carbon hydrogen stretching around 3100. And there's one more thing. This is the last thing that wasn't covered in the lecture class. If you have a mono-substituted aromatic ring, so that means it's only got one substituent, you will see stretches around 700 and 760 reciprocal centimeters. So we could circle this and say mono-substituted ring, aromatic ring, okay? All right, so that covers all the extra content that is new. So again, we looked at a few new things, few things that aren't covered in the lecture course in David Klein's book. But like I said, I highly recommend that you read our textbook, pages 110 to 117, before embarking on this assignment, because Dr. Schafzahl goes into a little more detail about IR than we do in the lecture course. Okay, and so these are most of the absorbances that you need to be aware of and that you need to be able to annotate for this assignment. Okay, are there any questions about IR before we move on to the mass spec? Okay, well, with that in mind, now we're going to turn our attention in the next 4 hours. We're going to look over mass spec, and I'm going to spend the rest of the lecture going over mass spec because in the lecture course, David Klein doesn't go into that much detail about the mass spectrometry of different functional groups, and that's kind of the treatment that I want to give it in this lecture. If you think about the way that we look at infrared spectrometry, what I would always do is kind of take a focused approach to each functional group and then discuss what would you see in the infrared spectrum of this functional group? What would you see in the infrared spectrum of that functional group? Well, if you look at the lecture course textbook, so the 3101 textbook, the only functional groups that really get that treatment are ketones, aldehydes with respect to the Mclafferty rearrangement, amines and alcohols with respect to alpha cleavage, and alcohols with respect to loss of water. So we're going to talk about some things that you would observe in the mass spectrum of other functional groups like carboxylic acids, ethers, okay, aldehydes. So let's get into it here. So mass spectrometry. Again, I want you to be sure to read Technique P in the lab book, in the Schafzahl textbook. Again, he goes into a little more detail than the David Klein book does. So be sure to take a look through that. Okay. You should know the difference between spectrometry and spectroscopy. And remember that we're bombarding molecules in mass spectrometry with a high energy beam of electrons. And so all kinds of things can happen in a mass spectrometer when we bombard a molecule with high energy electrons. We create high energy intermediates which can undergo fragmentation. And so that's why we see so many different peaks in the mass spectrum. And a skill that you have to develop is to be able to recognize what's an important peak and what is a peak that can be simply ignored. What are the kind of things that we can garner from a mass spectrum? Of course, molecular weight. If we have a molecular ion, right? This is simply a radical cation. We lose one electron. That can tell us the molar mass of the compound. And then from the molar mass, we can determine a molecular formula. Normally, we do that in conjunction with other kinds of spectra. Not always, but oftentimes we do. And of course, in this assignment that you're going to be working on that's due on the 26th of March, you're going to use infrared in conjunction with the mass spectra in order to determine the structure of some compounds. And then largely what I want to focus on today will be fragmentation patterns. Okay, what does it look like when you lose a methyl or an ethyl or an acyl cation or a propyl or a benzyl, right? Things like that. So that's what we're going to talk about today. All right. Again, we hit the organic molecule with a high energy beam of electrons. We knock an electron out to make a radical cation, and then that is going to fragment. But remember that only cations are detected by a mass spectrometer. A mass spectrometer is not going to detect radicals, just radicals that are uncharged. It detects only charged species, whether they're cations or radical cations. For example, if you take a simple molecule like propane, you'd hit it with a high energy beam of electrons. So this is, let's say 70 electron volts. You make a radical cation. That's what's happened here. Okay, there's our radical cation, and it has a mass overcharge of 44. Remember, we're dealing with low resolution mass spectrometry. The mass of a carbon is closest to its atomic mass, which is 12. The mass of a hydrogen is 1. So if we tally up 3 times 12, which is 36, plus 8 hydrogens, we get a mass over the charge of 1. 44 divided by 1 is 44. But how can this molecular ion fragment? How can that radical cation fragment? Well, it could lose simply a hydrogen radical to give you a mass overcharge of 43. That's a propyl cation. Or it could lose a methyl radical, right, in order to give us an ethyl cation. And these are the kind of things that we want to look for in our mass spectrum. How does a mass spectrometer work? Well, I'm not going to go over the whole details of this, but you inject your sample into the spectrometer, which causes it to ionize after hitting it with a high energy beam of electrons. Normally the sample is put into the gas phase by subjecting it to a high vacuum and usually elevated temperature, and then you simply detect the ions after they've been deflected by a magnet. All right, so let's get into fragmentation patterns and what we might expect to see in a mass spectrum. If we have a linear chain, for example, if we have something like, let's say, hexane, that's a linear chain. The molecular ion for something like hexane is going to be bigger than the molecular ion for something like 2,3-dimethylbutane. These two compounds are isomers of each other. However, since this one is linear, it's going to have a larger molecular ion. The intensity of the molecular ion tends to decrease with increasing molecular weight. Also, cleavage is going to be favored at branches, and the way that we determine which cleavage will be favored is based off of the stability of the cation that's produced. And we went over this in the lecture course, but you should know that as we go from a methyl to a primary to a secondary to a tertiary radical, stability increases, right, on account of hyperconjugation. All right, there we go. Oftentimes, we form resonance stabilized cations that are detected in the mass spectrum. I'm going to show you a few of those today. And sometimes we can lose small neutral molecules. The only small neutral molecule that we're going to focus on in this class that's going to be removed would be water from an alcohol. All right. So in class, in the lecture course, I went over alpha cleavage with you. I'm going to just quickly go over it again. So alcohols and amines are what's covered in the lecture course that undergo alpha cleavage. So this is the mechanism for alpha cleavage here. You don't have to have alpha cleavage necessarily memorized. Since we don't look at we haven't looked at radical mechanisms yet in the course. An easy way to do this, and this is a shorthand that was taught to me by Mr. Mayer, is if you have an alpha, beta, and gamma carbon like this, as long as when you look at the alpha and beta carbon, as long as you just draw a line of cleavage here like this, and say the side with the alcohol has a charge on it, that will suffice. If you want to practice drawing the mechanism for alpha cleavage, that is totally fine as well. But we're going to see several examples of alpha cleavage in both amines and alcohols today. Also, we went over the fact that alcohols can lose 18, which is the mass of a water molecule. We looked at the alpha cleavage of amines. Again, same thing. You look between the alpha and beta carbons, you draw a line, and that's the bond that breaks, and you end up producing a cation, which is detected in the mass spectrum. And then finally, the Mclafferty rearrangement. I'm not going to expect you to draw the mechanism of the Mclafferty rearrangement. There's no mechanisms required in this assignment. However, it's kind of interesting to look at it and to recognize that the Mclafferty rearrangement, what's lost, okay, has an even mass. even mass. If you think about anything that can lose an even mass in chemistry 3101 or chemistry 3102, the only even mass that you'll ever see that's not a Mclafferty rearrangement is the loss of water. All right, if we go back here, you see that losing water is a loss of an even mass of 18. So if you see any other loss of an even mass, you know that you have a Mclafferty rearrangement. Now, what's the requirement for a Mclafferty rearrangement? Pay close attention because this will be important. For a Mclafferty rearrangement, what the requirement is that you have either an aldehyde or a ketone that has an alpha, beta, gamma carbon, and that gamma carbon needs to have at least one hydrogen attached to it. Okay, so we could even write that down. Aldehyde or ketone with at least one hydrogen attached to gamma carbon. Okay, you could even frame that another way. You could say if you have a loss of an even mass in if you have a loss of an even mass, where the heck was I? I gotta stop reading this thing. Yeah, if you have a loss of an even mass in any mass spectrum that's not a loss of 18, you can pretty much assume that you have an aldehyde or a ketone and that it must have a gamma carbon with a proton attached to it. All right, now some of the fragments that we saw, not Avogadro's number of times, but many times in the lecture course were 15, 29, 31, 43, and 57. A methyl, ethyl, propyl, and butyl cation. Now the methoxy, I think it might have come up once, but methoxy is quite common as well when we have ethers or esters. So we're going to have to be on the lookout for that one as well. There are three more fragments that come up a lot in mass spectrometry, which don't really get a lot of attention in the David Klein textbook. However, they are going to be important today, and they are going to be important in our assignment. Those three are 77, 91, and 105. 77 is a phenyl carbocation. So that's simply a benzene ring that has lost a proton and has a positive charge. That's a phenyl cation. The next one is a benzyl cation. So if you were to take this molecule, a benzene, and put a methyl group on it like this, that molecule is called toluene. If you remove a hydrogen from there and you have a carbocation on that methylene, that CH2, this is called a benzyl cation. Remember, only cations or charged species are going to show up in the mass spectrum. And so this phenyl cation and this benzyl cation are going to show up in the mass spectrum. Now, something that you all should be able to do is draw the resonance structures of this benzyl carbocation. That's something that we would have done way back in chapter 2 of the lecture course. We even drew the resonance structures of this carbocation, and there are 3 more of them, and you should be able to draw all of those. I'm not going to do that right now, but that helps explain why the benzyl carbocation or the benzyl cation is so stable, and that's why it's so prevalent in molecules that have this fragment in it. Again, we're going to see some examples of that. And the last one is a benzoyl. Okay, so a benzoyl looks like this. We have our aromatic ring, and then we have a carbonyl, and we have a positive charge on the carbon here. Now you might say, well, it looks like the positive charge is on the oxygen there, Mr. Dion. Well, hold the phone. I can draw a resonance structure of this compound, right, where I delocalize these electrons. I put them down here. And again, I'm not obsessed with you drawing resonance structures on your assignment. However, I just want to show you that you would have the positive charge on the oxygen. So again, we see the resonance stabilization. And you might be wondering, can I draw more resonance structures? Yes, you can, absolutely. But that's neither here nor there right now. So again, the benzoyl cation, the benzyl cation at 91, and the phenyl cation at 77, okay, and benzoyls at 105. These are going to come up a lot. Once you get really well practiced and well versed in mass spectrometry, once you recognize or memorize these fragments, you're going to be able to look at a mass spectrum very quickly and make, very quick assumptions and assessments. I took a class on mass spectrometry when I was an undergraduate student, and I remember there was a guy in my class who memorized, I think the guy memorized every fragment in the textbook. And I remember we were going into the exam, and I said, Jason, what's this fragment? And he knew what it was. What's this fragment? I thought, oh no, I'm in trouble. This guy's gonna beat my brains in on this exam. Anyhow, so the more fragments that you know, the better off you are. But remember, when you're doing an assignment, what's great is that you can always refer back to this. You can also go to this table in our textbook, and you can see even more fragments. In fact, looking at mass spec fragments is something that most organic chemistry students can really grow to love. It's something that's really interesting and very logical. And so it's very appealing to a lot of students I've found over the years. All right, there we go. So I'm not going to spend a lot of time on hexane since we spent quite a bit of time on alkanes in the lecture course. Again, it's a good idea to have, these numbers memorized. I wouldn't even call them memorization once you've looked at them enough: 15, 29, 43, 57, 71. I mean, you're especially going to see these three a lot. Loss of a methyl radical, loss of an ethyl radical, loss of a propyl radical, right? We're going to see these a lot in the class. Also, you should know about isotopic clusters, or what we sometimes call the isotope effect, that is observed with chlorine and bromine. If you are the kind of person that likes to peruse the internet and look for more information about everything that we talk about in class, you'll find that there's all kinds of interesting information that you can learn from mass spectra in molecules that have one chlorine and one bromine, or two chlorines and a bromine. That, I would say, is beyond the scope of our course. However, you should be able to recognize the molecular ion and the M+2 ion for molecules that possess either chlorine or bromine. As you would have learned in the lecture course, if you have a molecule that's got chlorine in it, what you're going to see is the molecular ion, and you're going to see an M+2 peak that has a relative abundance compared to the molecular ion of about a third. Okay, so it's going to have about a third of the height. And if you're like, what are you talking about, Mr. Year? What do you mean? What I mean is this: if you have your molecular ion, what you're going to have is you're going to have an M+2 peak. That's not a third, is it? You're going to have an M+2 peak that's about a third of the height. Okay, and that's a dead giveaway that you've got chlorine in the molecule. Why is that? I'm not going to go into a long diatribe about that, but you should know the difference between atoms that are isotopes of one another. It's because of the difference in the number of neutrons in the nucleus. And so we have two abundant isotopes of chlorine, chlorine 35 and chlorine 37, and chlorine 37 only exists in about a 25% abundance with respect to chlorine 35. So here's a great example here. We have a chlorobenzene molecule, right? We subject that to 70 electron volts. That's a lot of energy. And right away, the first thing I notice is that we have two peaks up here. Not only is the molecular ion the base peak, so that's of note, okay? So the molecular ion is pretty stable, but also you see you have a peak at M+2 that's about 1/3 the height, right? If you compare the two, and you don't have to get a ruler out or anything like that, it's not that sophisticated, but you see that the height of the M+2 peak is about a third of this, right? It's about a 1 to 0.33 ratio approximately. So that's a dead giveaway that we've got chlorine. So let's say you only knew the molecular ion. What would you say? And you'd say, okay, it's got chlorine. What I would do is this: I'd get out my calculator, okay, to make sure I don't make any mistakes doing a back of a napkin calculation, right? If I said you've got $112, then you're going to remove $35. How much do you have left over? So you take 112, subtract 35, and you end up with 77. What was 77 based on that table we looked at a few slides ago? It was a phenyl cation. And so it stands to reason that we see this phenyl cation right here at a mass overcharge of 77. So there's chlorobenzene, and that's really all I want have for a take-home message for this slide. Bromine, I'll go over this one a little bit quicker. Again, bromine has two isotopes, bromine 79 and bromine 81. And so they have a nearly equal abundance. And so we have a molecular ion and an M+2 peak that have a relative abundance of about 1:1. So here's a beautiful mass spectrum of bromobenzene. We see that the base peak isn't the molecular ion in this case. However, you see the molecular ion, which is at 156. We have a nice, very nice peak at M+2, which is 158. It's a roughly 1-to-1 intensity. Therefore, right away, immediately, the student or the scientist could look at this and say, there's bromine in the molecule. So what would I do if I wanted to evaluate this? I would take my calculator out and I would say 156 subtract the most abundant isotope of bromine. So subtract 79. So if you take your calculator, 156, subtract 79, you end up with 77. What's that? That's the phenyl cation again. All right, there we go. So that covers isotopic clusters. Things to look for in terms of other halogens for an iodine. We don't have an isotope effect, so we don't have some kind of M+2 ion that we can look for and identify an iodine. However, you see a loss of 127 mass units on account of the mass of the iodine atom. So that's, I would say, pretty much a dead giveaway. The loss of 127 usually means we have iodine in our molecule. I don't even know if I've ever made a molecule. I've used lots of molecules that have iodine in them that I purchased from chemical suppliers, but I don't know if I can think of ever working in a program where I made a molecule with iodine. Anyhow, probably sometime in my life. Anyhow, here we have a mass spectrum of 1 iodobutane. You have your molecular ion up here, and you have that loss of 127, and you see the base peak is at a mass overcharge of 57. All right, well, I want to get into something more interesting in that, okay? Halogens are kind of cool. Losing alkyl radicals are kind of neat, but once we get into functional groups, it gets a lot more interesting and a lot more exciting, a little more rewarding in my opinion. So nitrogen rule, usually my students are pretty astute on the nitrogen rule by the time they finish this assignment. On every mass spectrum that is in this assignment, you should always refer to the nitrogen rule. And by that, I mean, if the molecular ion is even, you say no nitrogen present or an even number of nitrogens. If the molecular ion has an odd mass, I want you to unequivocally state there is an odd number of nitrogens, 1, 3, 5, etc. Okay? Be sure to include the nitrogen rule. Some compounds, don't show a good molecular ion. Things that are highly branched, like that 2,3-dimethyl butane that I showed you earlier today. If a compound doesn't have a good molecular ion, I will point out the molecular ion to you. So for example, oftentimes alcohols don't provide good molecular ions. I will indicate what the molecular ion is. I'm never going to leave you searching for a molecular ion, okay? It's not something that we do a whole lot in chemistry 3102. Maybe in majors organic chemistry, but not much in this class, if at all. Okay, so let's get into some functional groups. What about an amine? Okay, first of all, if you have an odd number of nitrogens, you're going to have an odd molecular ion, and we can also have alpha cleavage of the bond that's adjacent to the carbon-nitrogen bond. Let's take a look at the mass spectrum of an amine. So I want to skip ahead here to this molecule, which is 1-pentanamine. Now, some of these I'm going to go into more detail than the others, but I see that I only have 29 minutes left and I have a lot of content to cover here. So I'm going to have to talk a little bit faster, but I would rather go slower because I like talking about this kind of thing. But anyhow, remember that you're subjecting this molecule to 70 to 75 electron volts. That's a lot of energy, right? So you end up forming a radical cation. So I'm just going to draw a radical cation like that. And then that radical cation can undergo cleavage adjacent to that carbon-nitrogen bond, right? It can undergo the alpha cleavage. Let me go back here. We have our alpha carbon and we have our beta carbon here. Now, again, I'm not expecting you to draw radical mechanisms on here at all, but if you're the kind of person that's got an inquiring mind, you might want to practice that. So if we had that alpha cleavage, what would we end up with? We would end up with a butyl radical, which is going to have a mass of 57. That means that we would lose 57 mass units. Well, if I take 87 and I subtract 57, I'm left over with 30. And so my base peak, which would be nice if my students could identify in their assignments, would be what's left over. Well, what's going to be left over? I'm going to have a double bond to my nitrogen, which is going to have the two hydrogens attached. And so this is the ion that's detected as the base peak, is this ion here. Again, let me be clear. You do not have to draw the mechanism of alpha cleavage. Like I told you, Mr. Mayer kind of taught me some shorthands, and he said, look, you can simply draw a line between the alpha and beta carbon and just say, well, I'm going to lose this piece over here as my radical, and where I have my radical cation, that's the part that's going to be charged. And so very quickly, without drawing any mechanism for an alpha cleavage, you could say, well, I'm going to have this fragment, which is going to have a mass over charge of 30. There we go. So that's one pentanamine. I thought I had enough. No, let's go back here. I'm going to do a little skipping around here. The next one is an amide. So an amide, and again, there's more than one type of amide. We can have primary, secondary, and tertiary amides. For example, if you have an NH2 like this on your amide, this is a primary amide. If your nitrogen has one R group attached to it, this is called a secondary amide. And if your nitrogen has two R groups attached to it, this is called a tertiary amide. Again, things you would look for are the odd mass. You could look for the alpha cleavage of the bond adjacent to the carbonyl. Loss of NH2, right? That's got an even mass. I guess I misspoke earlier on when I said even masses are only the Mclafferty rearrangement and the loss of water, but loss of NH2, that would be a loss of an even mass. And that would only be from a primary amide, right? Loss of the carbonyl and the NH2, that's 44, which again is even. Okay, let's take a look at the mass spectrum of a primary amide. I have one right here. This is propanamide. That's the IUPAC name. The common name would be propionamide. So again, if you want to think about that alpha cleavage adjacent to the carbonyl, right, we would subject this molecule to 70 to 75 electron volts. We form our radical cation. Again, I don't expect you to draw mechanisms for these kinds of things, but what's going to happen is we're going to end up getting this kind of rearrangement. So we would lose an ethyl radical, and we would be left over with, I'm going to try to draw this without screwing it up, okay? Here we go. We're left over with something that looks like this. Well, an ethyl radical weighs 29. So a loss of 29, so 73 minus 29 gives you what? 44. There's my base peak. And so I know that this fragment, this ion, is what's producing my base peak. All right, there we go. What else do we see here? Is there anything else of interest? What was it? I'm forgetting something. Yeah, loss of NH2. So since it's a primary amide, let me just show you quickly. You do see the loss of NH2, right? NH2 weighs 16. If you take 73 and you subtract 16, you get this peak right here. So this peak is going to be due to, let's put it here, loss of NH2, okay? And so that would be due to this charged species right here, okay? All right, there we go. Bum, bum, bum. Again, when you're annotating your mass spectrum, let's say you're annotating the base peak, okay? Let's say you're trying really hard to annotate a base peak. I'll accept either one or both. You can either try to identify the cation, okay? So try to identify the actual fragment that's producing the signal or the peak, or you can do this. You could say, and this works totally is perfect, okay? If you just said loss of ethyl, okay, the loss of the ethyl radical, that would be good enough for me, right? Same thing here. You can draw out the charged fragment that produces the peak, or you could say loss of NH2. If you want to say both, that's fine with me too, okay? I'm the kind of person that likes to annotate, you know, if I have time, I like to annotate a spectrum and put all kinds of information on there, maybe a little too much. Anyhow, let's move on from there. This is benzamide. So this is the primary analog, amide analog of benzoic acid. Anyhow, If we look at the molecular formula of benzamide, you see it's got a molecular weight of 121, so it's got an odd mass. So right away, you'd write down the nitrogen rule. You'd say odd number of nitrogens, like that. Again, it's a primary amide, so you see the loss of the NH2 group, which would produce what? A benzoyl, right? A benzoyl cation. This is one of the fragments that we looked at today, 105, right? That's a very common fragment. Also, if you had the loss, if you lost the carbonyl, right? Loss of this, which it weighs 44, okay? You're going to have the phenyl cation at 77. Okay, I got to speed up. I'm going too slow here. How much time do we have? 21 minutes. Okay. I'm going to have to go a little quicker here. I'm going to draw a little less mechanisms moving forward and just kind of get down to brass tacks with you. Let's take a look at an alcohol. What else do we have here? Alcohol, molecular ion, sometimes small, sometimes non-existent. Again, I'm not going to leave you struggling like that. If the molecular ion doesn't show up in the mass spectrum, I will identify it for you. Okay. What else? Cleavage of the carbon-carbon bond next to the oxygen, so that's an alpha cleavage. Loss of a hydrogen, M-1. Loss of water, of course, M-18. I think I have an alcohol in here. Yes, 2-propanol. So again, this would be an alpha cleavage that's occurring here, the loss of the methyl. So again, you could put loss of the methyl, and you can just draw the radical like this, so loss of methyl. And you could draw, and again, I'm not going to draw the mechanisms, but if you could identify the cation, which would look something like this. Okay, if you can draw that, that's fine. This again is the charged fragment that has a mass overcharge of 45. What else? Oh yeah, the M-1 is shown here. You notice there's no molecular ion, so the molecular ion would be at 60. But again, I would give you that information on your assignment, so I'm not going to leave you out in the cold with that kind of stuff. What else here? We have a primary alcohol. So 2-propanol is a secondary alcohol. Here we have a nice primary alcohol. What do we see in the mass spectrum here? Look, we got M-18. What's that? You could say loss of H2O. If you look in your textbook, he will show you how to draw the radical cation that's left over from the loss of water. I don't really expect my students to do that, but it would look something like this. You'd have some kind of radical cation like that. Again, if you just write loss of water, trust me, Mr. Dion is going to be a happy camper, okay? I'd be very happy if my students would do that. What else? We have a big peak here at 31. So this is mass minus 43 here. So that's what ion is occurring here. And what weighs 43? Well, that would be the loss of the propyl. So if you just wrote loss of propyl, that's perfectly fine with me. If you can identify the charged fragment, okay, which looks something like that, more power to you, that's great. But again, for this class, if you just put loss of propyl, that's totally great. Next, we have an aldehyde. Oh boy, an aldehyde, cleavage of the bond next to the carbonyl. We can lose just a single hydrogen on an aldehyde. Oops, sorry, I lost you guys. What else? We can lose the whole carbonyl functionality with the hydrogen attached to it. That's what this is here. It's just the condensed formula there. So that's a mass. The molecular ion minus 29. Let's take a look. Is there an aldehyde? I thought it was benzaldehyde. Yeah, there's benzaldehyde here. Look at this. Aldehydes often have a big M-1 peak. Okay, might not always be huge, but you can clearly see there's a nice M-1 peak here, right? So you might say, oh, that's probably an aldehyde, right? Aldehyde. What else? We have the loss. We have the loss of the carbonyl and the hydrogen, which weighs 43. So you could say M-43 is what's shown here, and that would give you what? The phenyl carbocation, which I'm sure you recognize by now. What's next? I've got propyl benzene. What else did I have here? Was aromatics? Yes, aromatics. have big molecular ions on account of them being stable structures. If we go to this aromatic compound, though, it's got a pretty big molecular ion right at 120. So this is my molecular ion right here. Could anybody identify the base peak? And it doesn't have to be fancy. Could you type it into the chat or unmute your mic? Could anybody identify that base peak? This is one I would expect you to be able to identify and draw the charged fragment. If you're having a hard time seeing, it's got a mass over charge of 91. So if we zoom back out here, it's got a mass over charge of 91. Anybody can identify that? No? Okay, all right, is anybody there? If you go back to the table that we looked at a few slides ago, maybe 20 minutes ago or so, we saw 91, which is a really common fragment. Well, if you just do the math, 120 minus 91, right, going from here to here, this base peak is based on a loss of ethyl. So that's a loss of ethyl. Well, if I lost this ethyl, what would I be left over with that's charged? I would be left over with the benzoyl carbocation. So that's the identity of that fragment there. Okay? Okay. All right. Well, let's keep going. What's next? Oh, some other interesting functional groups. They have oxygen in them. So we looked at nitrogen-containing compounds, amines, amides. We looked at an aromatic. So those were all things that begin with the letter A. Now we're on to what? We got carboxylic acids, esters, ethers, right? I know my students can all identify a carboxylic acid, with one eye open, right, in the infrared spectrum. But what would we see in the mass spectrum of a carboxylic acid? What if you didn't have an infrared spectrum? What are the things that you would look for? Right, we would see cleavage of the bond next to the carbonyl, loss of the hydroxyl, which has a mass of 17, loss of the carboxyl, which has a mass of 45. Let's take a quick peek at a beautiful spectrum of acetic acid, which has a molecular ion of 60. You can see here that quickly you can do the math in your head for this one. This is a loss of a methyl radical, which weighs 15, right? Because it's M minus 15. And so the charged species that you'd be left over with would be this guy right here. Oops, we have a mass over charge of 43. That is a loss of the hydroxyl, right, which we said weighed 17. And so in that case, you'd be left over with this fragment. Again, if you just write loss of and what the species is that's lost, that's going to suffice for me. I would like you to try to identify the intermediates or the cations if you can. What else? An ester. Do I have an ester in here? Yes, we got methyl acetate here. Okay, so let's take a look at esters. Cleavage of the bonds next to the carbonyl. We can have hydrogen rearrangements. I don't think I'm going to get obsessed about hydrogen rearrangements for you. But the cleavage of the bond on adjacent to the carbonyl, that could happen on either side of the ester. And if you're like, what do you mean by that? Well, look, if you have this compound here, which is methyl ethanoate, that's the IUPAC name. If you were working in a lab, nobody would probably call it that. They'd call this methyl acetate, but that's neither here nor there. But what I mean is that you could cleave on this side or you could cleave on that side, right? Either one would be perfectly reasonable. If you were to cleave on this side here, that would be a loss of 15. So if you take 74, subtract 15, you end up with 59. So this peak here is going to be due to the loss of the methyl radical. I'm not going to draw the charged I'm not going to draw the cation. You could also cleave on this side here. So that would be the loss of the methoxy radical, like that, which weighs 31. Okay, and again, you guys could draw the charged intermediates if you want. Let's see here. For an ether, what did I put here about ethers? Cleavage alpha to oxygen, carbon next to the oxygen. So that means we could cleave, you know, this one's symmetrical, so we could cleave here, we can cleave here, either way on an ether. Did I put anything in here about that? Yeah, I had written something down about that. So what do we have here? So if we take, we have 102. So we have big signal here at 43. So that's 102, subtract 43, which gives you 59. So that would be a cleavage of the blue bond here. Okay, so that would be, this would be due to the propyl radical, and then it would be loss of, and you know, as long as you do your best to draw this, so it would be loss of this radical. Okay, what else do we have here? If we break on the red bond here, that would be due to the loss of, let's see here, so that would be a loss of 43, right? No. Loss of 29. Oh, sorry, did I draw the wrong one here? So, sorry, my mistake. When I said loss of the propyl, that would be where the, yeah, it would be right here. Sorry, my mistake. There we go. And then if we have 102, subtract 73, we have loss of 29. And that would be losing this guy right here. Okay, so this would be loss of the ethyl radical. There we go. All right, so that's for 73. There we go. So that's an ether. Here we have a ketone. Did I have ketone in here? I think I did. Yeah, ketone cleavage of the bond next to the carbonyl. So in a ketone, we could have cleavage on either side. We could have cleavage here. We could have cleavage here. Again, I would try to draw those cations, those charged species that are detected in the spectrometer. So if you were to cleave on the red, where the red line is, that would be the loss of an ethyl radical. So this would be loss, oops, I should try to be color coordinated here, right? This would be loss of the ethyl radical, CH3, son of a gun, CH3, CH2, there we go. So that would be loss of an ethyl radical. Then if you lose 15 on where the blue bond, where the blue line is, that would be the loss of the methyl radical, right? M minus 15. So if you take 72 minus 15, you get 57. If you take 72, subtract 29, right, which is the mass of an ethyl, you end up with 43. Again, I'm not going to take the time. Well, maybe I could draw it. So if you lose 29, you would be left over with this guy right here, and you can draw the resonance structure of that anyhow. Let's move on from there. So, all right. Let's see here. Where things cleave. So you should know what kind of effect a functional group is going to have on cleavage. I mean, we're really just touching the tip of the iceberg in terms of different fragmentation patterns that can occur in mass spectrometry. I mean, of course, if you look at really complex molecules or biomolecules or proteins, I mean, that's a whole other kettle of fish, which is something that we don't even concern ourselves with here. Also, we don't discuss HRMS, which is covered a little bit in the lecture course. There's a section in our textbook about that, which we don't go over. What else? I'm absolutely expecting you to recognize the nitrogen rule, isotopic clusters. I would like you to try to identify base peaks. Okay, not only what the loss is, but if you can draw the fragment, that would be great, the fragment that's detected. And there we have it. You know, that's kind of the basics of mass spectra. You know, what is the process that you would use for interpreting a spectrum? Well, it depends on the person. It probably depends on the day. But here's sort of a breakdown of an approach you might want to have. You know, sometimes students might look at a mass spectrum and just immediately be intimidated. They see all these lines. But remember, one of the things you've got to be able to do is to distinguish signal from noise, right? You have to be able to recognize what's important? What's the good information that's going to help me determine the structure of the molecule? The first thing you want to determine is the molecular ion. You want to evaluate it in terms of the nitrogen rule. Look for the presence of a halogen, nitrogen, of course. Look for those common fragments and patterns. What were the common fragments, right? A methyl at 15, an ethyl at 29, a propyl at 43, a butyl at 57, right? What would a pentyl be? 69, right? Those kinds of things. A phenyl, we saw that at 77, a benzyl at 91, a benzoyl at 105. These are very common fragments in this class. You want to come up with some kind of molecular formula and postulate a structure that's consistent with the known data. Look, let me just address one thing here that I'll see students do sometimes. Is when you're coming up with a structure, don't just guess and start drawing bonds anywhere. Now, I'm not going to draw an incorrect structure. I don't like doing that, drawing things that aren't correct. I did that this morning with my students. We were talking about mechanisms, and I was saying, you know, a carbon can't have 4 bonds, and we talked about why that is. But ask yourself, does your structure make sense? This is something that, you know, your lab instructors and I notice from time to time. The students will submit structures that have no bearing in reality whatsoever, a structure that simply can't exist. Now, if you're thinking, you know, what kind of things can't exist? Well, if you're inventing new functional groups, or, you know, if you're drawing oxygens with 3 bonds that have no charge, right? These are the kind of things that you want to think about ahead of time, okay? And if you have a question, you know, you're wondering, is this reasonable? Something you might want to do is calculate the formal charge of the atoms in your structure and say, okay, well, is this reasonable? Do I have no charges on any of my atoms here? Because we're not going to be looking at any charged molecules, you know. Anyhow, just something to think about. It's something that I see sometimes, and it really gets my mood down when I see students give me molecules that don't even make sense. So try to draw something that's reasonable. Here I have a couple of mass spectra I'll take a look at. We don't have a ton of time right now, so we'll start with the easiest one of all. So there's a couple of examples here. I just tack these on at the end, time permitting. And again, this is the simplest one of all 4 of these. And I think it's also the most pertinent to us because we have a mass spectrum and we have an infrared. But imagine I gave you this, okay? Now, to a seasoned organic chemist, she or he could probably figure this compound out in a minute, like less than a minute. But to somebody who's just learning, it's going to take you a little while. I want to ask my students, let's not even worry about the mass spec yet. Is there anything that you see, any functional groups that you recognize in the infrared? Anything there that kind of just is immediately grabbing your attention? Any functional group? All right, great. I see some really good answers. Yes, you're both in the right vein, I think. Yeah, I see Josh says a carbonyl and Byron says an alkene. There's not an alkene per se in this molecule, okay? But I see where you're going, Byron. You know, it looks to me like we have some aromatic carbon-carbon stretching right here, doesn't it, right? Between, what did I say? Between 1475 and 1600? Yeah, I'd say that. Okay. Also, Josh said there's a carbonyl stretch here. Yeah, absolutely. Well, I know that this range of signals here might not be as big and bad and broad as some of the oxygen hydrogen stretches that we've seen, but this is the oxygen. This is an oxygen hydrogen stretch right here. And so in this molecule, I'm going to go over it really quickly because I only have 3 minutes left. We've got a carboxylic acid. Okay. We've got that functional group, and we also have an aromatic. Okay, you could also argue that this here is sp2, carbon hydrogen stretching here. So we also have an aromatic ring. Cha-cha-cha. There we go. All right, so we got those 2 fragments. Now we've got a mass of 122. We've got no nitrogen or an even number of nitrogens. What else do we have in this mass spectrum? We've got a big old peak at 105, right? This is 105. What's 105 that we saw a bunch of today? a benzoyl cation, right? We also have a peak at 77, which is a phenyl carbocation, right? All reasonable based on the fact that we have an aromatic ring and a carbon hill. Well, if you tally up the mass of a phenyl cation, which is 77, and you add that to the mass of a carboxyl group, which weighs 45, if you take 77 plus 45, you get 122. So that means all we have to do is put these two fragments together like that, and we get this molecule here, which I'm sure most of you recognize from the recrystallization experiment. This is benzoic acid, which I know some of you recrystallized this week from water. Okay, but that's the kind of approach that you want to take. We recognize the functional groups, an aromatic ring and a carboxyl group, and then we also recognize some fragments in the mass spectrum. We recognize that there's no nitrogen in the molecule, and we were able to put those two fragments together to make this molecule, and therefore we have proposed a reasonable structure for these two spectra. All right, we have 1 minute left, and I'm going to have to cut it off there. Are there any questions about the assignment, I guess, would be probably what my students are wondering most. Are there any specific questions about the assignment? Where's my stuff presenting? Any questions? So remember, I want you to print it out, annotate the infrared spectra completely with the annotating the functional groups. I want you to annotate the mass spectrum. Always write down the nitrogen rule. If there's an isotope, I want you to identify, is it a chlorine or a bromine? I'd also like you to identify the base peak, if possible, and any other major fragments. You can write loss of things like a carboxyl or a hydroxyl or loss of ethyl, methyl, things like that. If you can try and identify the fragment that's producing the peak, that would be just wonderful. We'd really like that when our students are able to do that. And of course, if you have any questions, feel free to email me, or you can email your lab instructor. If it's Mr. Mayer, you could email him. If it's Miss Herring, you could email her. And yeah, that's really it. Again, if there's any questions, feel free to contact me, and I'd be happy to address those.